Today we're going to talk chemistry basics. This will be probably one of video 2 or 3. We'll see how quick it goes. But we'll talk observations, qualitative versus quantitative. We'll talk about inferences a little bit. We'll talk about the 3 states of matter. We will talk about phase changes, and then of course the difference between chemical changes and physical changes. So here we go. Let's start with observations versus inferences. I love this picture because it proves the point, talking about observations and inferences. What observations can we make in this picture? Well, I see there's a goat. I see there's a boy. I see that there is a broken tree branch. I see there's a pond that the boy is in. We have a nice pasture and trees and all that and a fence. I see that the boat's in the water. So those are all observations. What did I just do there? I just used my sights, my senses, right? In this case, sight, and I made some qualitative observations. Observations with words, right? We can also make quantitative observations. Maybe I could say there's 1, 2, 3, 4, maybe 4 branches off the main branch there. I could say the goat has 2 horns. I could say there's 3 rocks in the water. I could make some quantitative observations as well. But what is an inference? Well, I think we can all infer that some reason that the boy fell in the water, right? So inferences are what I believe to be true based on the observation. So there's a broken branch, there's a boy in the water, those are observations, but how did he get there would be an inference. So I could make an inference that say the boy was climbing on the branch and it broke, he fell into the water. I could say the boy was maybe reaching for his sailboat and the goat came over and pushed him in. Do I know that happened? Absolutely not, but I could make an inference. So in science, we want to be careful about making inferences when we should be making observations, right? Using our 5 senses to simply describe a truth. Sometimes we'll want to make inferences, but a lot of times it will just be observations. All right, moving on, matter, right? This is anything that has mass and takes up space. We're going to be talking about 3 types of matter in a second, but matter is simply that, anything that has mass. We could put it on a balance somehow and get a number out, and anything that takes up space, and this means volume, whether it's a solid, a liquid, or a gas. Matter is just that. Okay, the 3 states of matter, right? I'm going to be drawing this a little bit, so give me some grace on this, but let's start with our friend, a solid. Okay, so 3 states of matter. When we're talking about a solid, we want to think about how these things look on the molecular level. So you've heard me refer to it as magic school bus level, right? So we're looking at the molecular level of water or any solid, I guess. So it would be an ice cube, right? But let's talk about solids. Solids have a definite shape, as you see this block of whatever does, and a definite volume, meaning we could take the length times width times height of that and come out with a definite volume, right? And solids aren't just still. We could pick up a pen or a pencil, and it looks like it's not moving, but in reality, this would be tough to draw, but this is real tough to draw. Solids vibrate in place, and those are supposed to just be the vibrations coming from them, so pardon me. But solids vibrate in place, they're packed closely together, and that's what makes a solid a solid. Solids have a definite shape and a definite volume because they're packed so closely together at the atomic or molecular level. So awesome. Let's move on. Maybe try a different color here. I'll come back to that color. Let's try blue for liquids. That makes sense, right? Liquids are second state of matter. We'll use this beaker again, and we'll look on the magic school bus or molecular level, and you should see a big difference here. These molecules of whatever liquid we're talking about are a bit more spread out. They're still close together, but they're a bit more spread out. And liquids take the shape of the container that they're in, whether they're in this beaker here or whether I pour them out of the beaker onto a desk. They're going to take the shape of whatever the container is. They still have a definite volume, but they don't have a definite shape. And the reason is because these molecules, I'll draw some arrows here, I like to call it, they flow freely. And you know liquids flow freely, right? Imagine we tipped both of these beakers over. What's going to happen when you tip this solid beaker over? Well, that solid's just going to fall out. It's because those molecules are packed so closely together. What's going to happen to this liquid? Well, those molecules are going to flow out and take the shape of whatever they fall into. That's because liquids are spaced not as close together and they can flow past each other. All right, let's use this last color for gases here. You know gases. Gases are crazy. They're spread out and they're erratic. They're moving everywhere. They're bumping into each other. They're going the other direction. Gases are erratic. And because of that, gases take not only the shape, but the volume of whatever container they're in. Whether we're talking about the atmosphere or this beaker or the room you're sitting in right now, gas is there, it's moving around, they're bumping into each other. Gas is erratic because of what the molecules are doing. They're moving around fast, they're bumping into each other. So those are your three states of matter: solid, liquid, gas. All right. State changes. So we can talk about solid, liquid, gas, and we can go from one state to another. And I'm not talking about states of the union, but I'm talking about states of matter. So let's go solid in the middle, solid on the left, liquid in the middle, and gases on the right. Okay, so what can we do? We can, I'll use blue for this one, we can go from a solid to a liquid. We're adding energy or adding heat when we're doing that, and we call that melting. Right? We can keep going from a liquid to a gas by adding more energy, and we call that evaporation. Evaporation. Come on, dot. There we go. All right, so now we can go back the other way. And I'll change color for this. We can go back the other way, and we are taking energy out of the system here. Going from a gas to a liquid is condensation. And going from a liquid to a solid, we call that freezing. Again, taking energy out of the system. So solid, liquid, gas. We can do one more, and this is kind of a special one. I'll use red for this. No, I'll use blue for this, because if I can find my blue, here we go. Because we're adding energy, we can go straight from a solid to a gas, and we call that sublimation. And dry ice is a great example of sublimation. When we allow dry ice out of whatever container it's in, it's going to go straight to a gas. It's going to skip that liquid phase. Okay, physical changes versus chemical changes. This is a big topic to know. Let's talk about a few things. Number one, the first thing you have to ask yourself in physical changes versus chemical changes is this question: is there a new substance formed? This is really question one. If you can answer this, you should be good. If there is a new substance formed, then we have a chemical change. Those atoms have rearranged and have formed a new substance, right? If you're answering no to this question, it's a physical change. And a lot of times people can get confused about these because they see something like water turn into ice, right? Liquid water turn into ice. Well, it looks like a new substance, but it's really not. It's still H2O, right? It's not a new substance. It's still water. So, moving on. A second question you can ask yourself is the process reversible? right? So if I take liquid water and I turn it to ice, take energy out of it, put it in the freezer, can I reverse that and get liquid water again? Of course you can. We would call that a physical change. It's a phase change. It's reversible. Though a chemical change, if I took a piece of paper, lit it on fire and burned it, can I get that piece of paper back to its original state? Absolutely not. We now have new substances there. That paper is now smoke and odor and flame, right? It is a new substance has been formed. You can't get the old back. Okay, really important. Last thing we'll talk about is evidences of a chemical change. How do we know that a chemical change has happened? Well, we said, is there a new substance formed? But some clues can help us with this. Here are the 6 that you have to know. I'll kind of give you some pictures with each one and talk through these. So number 1, odor, right? We see this in the kitchen, baking, cooking. We're taking food. We are heating them up at such a rate that these foods still become the same food, but their chemical composition changes. And what do? They give off an odor. That odor hopefully is usually good. Sometimes it's bad, but is it reversible? Can we get that food back? If we mix flour and sugar and eggs, can we get that back to flour and sugar and eggs once it's become a cookie or a cake? No, absolutely not. That would be a chemical change. How about a color change, right? Leaves in the fall, that's a color change. That's a chemical change. Can we get that back? Well, no, not without the leaf dying, falling off the tree. We need a whole new leaf there. So that would be evidence of a chemical change. Gas produced, right? This one's a very, very common one. When we have a chemical change, we see bubbles. That gives off gas, maybe a smoke. That's a good evidence of a chemical change, that we have a new substance formed. How about a temperature change, right? An explosion. Again, we see this in cooking and baking. Do we have temperature change? That's a good evidence of a chemical change. Now that one can be tricky, because I can heat up my water and let it boil on the stove, and that goes into a water vapor, but is that a chemical change? No, it's a physical. So you have to be careful with some of these. It's not all or nothing. Some of these could be both, but a temperature change will always happen in a chemical reaction. Precipitate. Precipitate, let's go ahead and write down this definition. Make sure you know what a precipitate is, and it is a solid formed from, slowly but surely, 2 liquids. And you see the picture to the right of this writing. I'm pouring 2 liquids in, so I'm pouring one clear liquid and another liquid, and we see this nice yellow substance. That's actually a solid. It will take a little bit of time. It will settle to the bottom, and you can see it a lot better. But that's precipitate. That's evidences of a chemical change or a reaction. And finally, light, right? We see this with fire. We saw it in the explosion as well. Light produced is a good evidence of a chemical change or a chemical reaction.